Hi there. In this video, we're going to talk about the Laurent series and residues. In the previous videos on complex analysis, we've considered the Maclaurin series and the Taylor series as expansions of different complex variables. We saw that the Maclaurin series has this particular form, and the radius of convergence is actually centered at the origin. So that is the radius of convergence of the Maclaurin series. We saw that a limitation of this is that we can have a singularity on the boundary of the circle and perhaps even within the circle of convergence. So how we dealt with this issue was considering the generalized form of the Maclaurin series, which is the Taylor series. With the Taylor series, we can move this circle of convergence to, instead of being centered at the origin, to be centered at some other arbitrary point, maybe z0. So in this way here, we have now considered some kind of series expansion outside of our singularity. And of course, the only difference in the actual expansions is that where we would have 0 in the Maclaurin series, we substitute that with our arbitrary point, that's z minus z0. Now we consider a situation in which we no longer just want to consider the series expansion around a point, okay? We want to consider the series expansion specifically around the singularity. So that's what we want to do. We now want to expand some kind of series, a polynomial series, around our singularity itself. So in the Taylor series, it doesn't really help us because we had used it to move the circle of convergence away from the singularity. So then what do we do? Well, what we're going to do is to start by considering what we're actually doing. So we have our z-plane, and we have our singularity, and it's at some point z0. So we have two curves. This curve, we call that the outer curve. Maybe we'll call that C1. Just around the singularity itself, we have another curve. So we'll call that maybe C2. Okay, I'll just draw it a bit bigger. So that inner curve is C2. So our region that we're considering in this particular scenario is actually between these curves C1 and C2. So it's actually this region inside. So this is an annular region. And when we are considering a contour or some curve or something like that, it's actually falling in between these two curves. So in between C1 and C2, we have some generic curve C, which we'll be applying this analysis to. So just to repeat it once more, Z0, that is our singularity. And we are analyzing this system in which we are now going to write the series expansion about C. So C is the closed curve. And we'll also need to say that f of z, some function, is analytic. So it's analytic in this annular region. So this region that's highlighted in red is analytic. Analytic in annular region. So how does the Laurent series actually look? What form does it actually take? Well, it's actually very similar to the Taylor series that we've seen thus far. There are some differences, but let's just write the generic form of it. So we have our function fz. In this Laurent series, we're going to have a term a0 that would be associated with some subscript n being 0. Then we would have a1, that's another coefficient with n equal to 1. And we would have z minus z0, and we would have plus a2 into z minus z0 squared, and it would carry on in this manner. However, the series expansion doesn't start with n equal to 0, whereas the Taylor series and Maclaurin series would start with n equal to 0. This one actually starts from minus infinity. So we have terms to the left of this a0. So what are the terms to the left? Well, it just carries on in that same manner. We have z minus z0 now to the power minus 1. And the coefficient in front of that term is a minus 1. Here's a is equal to 0 and here a is equal to minus 1. And it will carry on in this manner. So it goes on from infinity. Maybe we could write another term. We'll have a minus 2. Then we have z minus z naught to the power minus 2. And it carries on like that. So if we were to write a generic form of this Laurent series, what it would actually look like is f of z is equal to the sum where n goes from minus infinity to infinity of a n, okay, these coefficients, into z minus z naught to the power n. So this series can be easily evaluated if we know these coefficients a0, a1, a2, a minus 1, a minus 2, and so on. So we can derive some general expression for an, and we can do that now. We can just compare it firstly to the Taylor series. Here's our term z minus z naught. So if we go back up to the Taylor series, there's our term z minus z naught squared. So whereas the coefficient was this second derivative at z naught divided by 2 factorial, it's just essentially been lumped into one coefficient. So as I was saying, what we're going to do is derive an expression for this an, and some interesting results come out of this whole thing. So the first thing I'm going to do is replace this index. I'm going to replace n with m. So we're going to have fz is equal to this sum, where now m starts from minus infinity and goes to infinity. And we're going to have am into z minus z naught to the power m. So why have I done this? Well, I'll need to compare m and n at some point. They are the same, they are equal, but I have to state that in a specific way to get a certain result. So the first thing that we're going to do in this derivation is that we're going to divide both sides of this equation by z minus z naught to the power n plus 1, okay? And we divide the right-hand side, so we have z minus z naught to the power n plus 1. So I just simplify this right-hand side, so I'll get f of z divided by z minus z naught to the power n plus 1, and then that will equal to, this sum remains the same, we're going from m minus infinity to infinity, and this coefficient am, and then we can just simplify this. We have z minus z naught, we have this m, we take this n plus 1 to the top, it becomes minus n minus 1. So what I'm going to do now is I am going to multiply both sides by the differential dz. Then I am going to integrate both sides, around this closed curve C. I do that for the left-hand side, and now I do it for the right-hand side. I integrate around the closed curve C. And let's just remind ourselves what that closed curve C is. C is that orange line in this annular region. So now that I've done that, I can proceed with this derivation. And the first thing that we must realize is that since it's happening within the analytic region, this is actually going to converge, okay? So this sum is going to converge. And since this integral and the sum, well, it's converging in that around that contour, we can actually swap them around. So that's what we're going to do. We're going to swap around this integral and this sum. So we're going to write integral here around this closed curve, and then the sum as m goes from minus infinity to infinity. So now that I've done this, I need to evaluate this integral on the right-hand side. So this integral now that I've indicated in the square brackets, I want to evaluate that. So I'm going to bring that out. So I have integral now around this closed curve of C of a m into z minus z naught to the power m minus n minus 1 dz. So this is a result that, or the result of this integral is something very important in complex analysis, okay? We have to consider two scenarios. The first scenario is where this index m minus n minus 1 is equal to minus 1. So this integral, this index m minus n minus 1, this exponent, sorry, where this exponent is equal to minus 1. So when this exponent is equal to minus 1, what we're actually saying is that m is equal to n. Okay, this is very obvious to see. So we're now going to evaluate this integral for this particular scenario. We can take this am out of this integral. We can put that as part of the sum. So what we're evaluating now is the integral around this closed curve of z minus z naught to the power minus 1. Okay, as I said before, or just now, was this exponent takes on the value minus 1. So we are evaluating this integral where this exponent is minus 1. So how do we go about doing this? You might ask at this point, okay, isn't the integral around a closed path of some kind of complex variable, isn't it just 0, right? Isn't it just 0? Well, it's only 0 if that region is analytic. Remember the Cauchy-Gaussat theorem we had looked at in the previous video? So that only applies if we are considering the entire region being analytic. In this case here, we have a singular point. So we're considering now where we have a curve and we have a singular point singularity inside it. So in that instance, the Cauchy-Gaussat theorem does not apply. Okay, so this integral does have a value. So how do we evaluate this integral? So what we're going to do is we're going to let this z minus z naught equal u. So we let u equal z minus z naught. We have done a substitution. So if u is equal to this, then it means that du is equal to dz. And also, since this is a complex variable, we can also say that u is equal to re to the power j theta. Okay, this is the polar form of a complex variable. So this is what we're going to use to evaluate this integral. So this integral now around this closed path of z minus z naught to the power minus 1 dz. So that's just equal to this integral around this closed path of c of u to the minus 1. Okay, u to the minus 1. We will write that as 1 over u now times du. So if du is equal to dz, then du is also equal to this derivative of this re to the j theta. And if we take this derivative, then what we get is the exponent of e to the power j theta is just e to the power j theta. Remember, our changing variable here is theta. R is just a constant and j is the square root of minus 1. That doesn't change. So if we're taking the derivative of du, then theta is our variable. So j theta is our inside function. So what that means is that the derivative of the inside function is just j. So we're going to have j times r. Okay, just to repeat that once more, derivative of du is equal to re to the j theta. Derivative of e to the power j theta is e to the power j theta. And the derivative of the inside function is just j. So we multiply it by the outside using the chain rule. So now we substitute all of these things in. We have the integral around this closed path of c of 1 over u. So we have 1 over re to the power j theta. And now we multiply this by du. And du is jr e to the power j theta d theta. So we write that out. We have re to the power j theta times d theta. So what do we see? This e to the power j theta, e to the power j theta cancel off. Sorry, there's a j here as well. I just need to write that. I'll just write that there. Okay. And this r cancel off. Okay. So all I'm left with is just j. I have integral of j d theta, and now integral around a closed curve. So we have a closed curve and we have theta. So what is the integration bounds of a closed curve? The closed curve is just 0 to 2 pi. Remember that there's 2 pi radians in the circle. So one complete circle is just from 0 to 2 pi. So we have j d theta. There's j here and there's d theta there. So this integral you can easily see is just j times 2 pi. So that's what this integral is. So we can write that as an important result. That important result is that this integral around the closed curve of z minus z naught to the power minus 1 dz, this thing here is simply equal to j times 2 pi. So that was the one scenario where this exponent inside this expression was minus 1. So what about everything else? What about when its exponent is everything else besides minus 1? So we have this integral now. We have this integral of z to minus z naught of m minus n minus 1. And now we have to consider the scenario where m minus n minus 1 is not equal to minus 1. Okay, so this is the scenario where m and n are not equal. So when m and n are not equal, all that happens now is that this entire integral becomes 0. This whole integral becomes 0. So that is an important result. This is another major important result. How would we prove that? We would prove it in the exact same way that we had done this year. Okay, so I'm not going to do the full proof. It's a simple thing to do. It follows the same procedure. So we let u equal to z minus z naught. And now, if we're saying that m minus n minus 1 is not minus 1, then we have this integral now around this closed curve of u to some index, okay, to some index. We'll call that k, and maybe this would be m minus n minus 1, okay. So it would be u to the power k. And now we would do the exact same thing. We would now need to do this r. So instead of now u equal to r e to the power j theta, as it is here, right, we would now need to have u to the power k, okay? And now we'd raise all of this now to the power k, and we would carry on in this fashion. But the moral of the story is that all of this becomes 0. So you can proceed with that proof or look it up in a textbook or something like that. So in any case, this thing is equal to 0. So now we have our expression for this coefficients of this Laurent series. This is where we are. We are here. We are here. We wanted an expression for this coefficient. Okay, so let's just proceed from that point so that we don't lose track of where we were. So the last thing that we had written was that we have this integrals that we are evaluating. We have this integral around this closed curve, this left-hand side, and that was fz dz divided by z minus z naught to the power n plus 1. This is now equal to our integral around this closed curve. Sorry, we had interchanged the sum and this integral. So we have sum where we have m and n, and now we see from our results here that since we are only considering the scenario where m is equal to n, which gives us this value j2 pi, this is all that we are considering, right? We are only considering the scenario where m and n is equal, because everywhere else where m and n are not equal, this integral gives us 0. So there's no point in considering it. So we are only considering where m is equal to n, and that's why we have now replaced this m with n. And n is going from minus infinity to infinity of an. Now this integral around this closed path of z minus z naught, okay, m minus n minus 1 dz, okay. And we saw that this entire thing is the same, so we just replaced this with minus 1. M minus n is the same, so this becomes minus 1. And we saw that now this entire thing, so let's write the left-hand side first. We have fz dz. Now we're dividing that by z minus z naught to the power n plus 1. This is equal to, firstly, okay, we saw that this integral is 0 everywhere else besides where m is equal to n, and it just takes on that value n. So this sum doesn't have any meaning, because this integral is only going to give us one specific value. It's going to give us j2 pi only where we consider the value n. So we're going to replace all of this with an, okay, that's the coefficient here, and the sum of this, remember that this means sum of the integral. So we compute the integral for different values, okay, and we would take the sum of it. But it doesn't make any sense here at all, because there's only one value that is valid, and that is for n, and it takes on that value j2 pi. So we would have an then multiplied by this integral, which is j2 pi. Just write the j in front, and we have times 2 pi. So all we do is we solve for an. And when we solve for an, then what we get is that this thing is equal to 1 over j times 2 pi times this integral around this closed path of f of z times dz divided by z minus z naught to the power n plus 1. Okay? We can just remind ourselves what we're doing. We're doing the Laurent series, and the Laurent series f of z is equal to expression from minus infinity to infinity of a minus 2 z minus z naught to the power minus 2. Then we carry on a to the minus 1 z minus z naught to the power minus 1 plus a naught plus a1 z minus z naught to the power 1 and so on. Okay, so all of this coefficients can be evaluated using this expression that we have derived. Okay, we can write it like this. So what we're going to do now is something interesting. Okay, we are now going to integrate fz. We're going to take the integral of fz around that same closed path. So we're going to integrate fz dz around that closed path of C. And we're doing this with fz, so we can do this with each term of the Laurent series. And if we do that, we have the integral around this closed path of a to the minus 2 into z minus z naught to the power minus 2 dz plus a minus 1, integral around the closed path of a minus 1 into z minus z naught to the power minus 1. There should be a dz here as well, plus this integral around this closed path of a naught times dz plus integral around the closed path of a1 z minus z naught to the power 1, and we carry on like that. Okay, so does it make sense to do all of these integrals? Does it make sense to evaluate all of them? No. If we do that, we will be wasting our time. Why will we be wasting our time? We will be wasting our time because we saw just now that when we evaluate this specific integral, z minus z naught to some indice, it only has a value when this exponent is minus 1. So if I just scroll up a little bit here, we saw in this derivation that we have a value for this integral, okay, this integral, only when this exponent is minus 1, and it's that value j2 pi. Everywhere else, for every other exponent, this integral is equal to 0. So what this means is that the integral around this closed path of fz dz is equal to 0. It's 0 for all terms except where this exponent is minus 1. Z minus z naught to the power minus 1 dz plus 0, and everything else is 0. Okay? And what's the value of this integral? This value of this integral is simply j2 pi, which we had derived earlier. So this thing is just j times a to the minus 1 times 2 pi. Sorry, not to the minus 1. It's a of minus 1. So this a minus 1, that is given a particular name. So the name that it is given is a residue. It's called a residue because residue means what's left. So when you integrate the series expressed as the Laurent series, all you get is this term here with this coefficient a minus 1. So it's what's left when you integrate this function expressed as the Laurent series. So this is what the residue is. So this is the end of this video. Thank you very much for watching. In the next video, we're going to apply this to an example, and we're going to see exactly how we calculate residues for poles and that sort of thing. So thank you.